Okay, so in the earlier videos of chapter 2, we discussed the passive filters, where the maximum gain was 1. In this video, we will talk about the active filters, where the gain will exceed 1 with the help of the amplifiers. Okay, so we will talk about the low pass filter, active low pass filter, the active high pass filter, and the active bandpass filter. The general equation of the active low pass filter is the same as the passive. However, we have a minus k. Okay, in the passive filters it was only k. Here we have a minus sign. Why minus? I will discuss it later on. Okay, we have a minus sign in here. The circuit of the active low pass filter is as follows. Here we have two resistances, okay, and the capacitor on the feedback resistance, which is R2. That's an active low pass filter. Okay, for the high pass filter, the general equation is the same as in passive, whereas we have the only difference is that we have a minus sign. Okay, and for the circuit, the capacitor is with the input resistance rather than the feedback resistance. Okay, and it's in series. For the low pass filter, it's in parallel. Okay, for the last filter, the bandpass filter, active bandpass filter, the general equation is still the same with the minus sign. Okay, and as we said earlier, that the bandpass filter is a combination of low filter and the high filter. And here you can see this is the low pass, active low pass. This is the active high pass, and this is a general inverting amplifier. Okay, now we said that in active filters the gain will exceed 1. Okay, now note that there are no inductors for the active filters. All of the components are either resistance or capacitor. Okay, one of the reasons that there's no inductor is that inductors are expensive. This is one of the reasons. So omega c here, omega c will always be 1 over rc, right? Because the omega c is either 1 over rc or it's r over l, and as we do not have an inductor, it will always be 1 over rc. Okay, now let me give you a review on the amplifiers and how we solve them. Sometimes they are called op amps, operational amplifiers. Op amps. Okay, now this is one of the op amps, one type of the op amps, and it's called the inverter. Why is it called the inverter? I will tell you now, just in a second. Okay, there's another resistance here, and this is the output. Okay, now this resistance, we will call it the input resistance. Input resistance. The input resistance. This is called the feedback resistance. The feedback resistance. Okay. Now, this amplifier is called the inverting amplifier. Because it swaps the sign, it flips the sign of your input. For example, if my input voltage is 1 volt, the V output will be negative the number. Okay, so it will always be the opposite sign of the input value. That's why it's called inverting. Now, how do you know if it's an inverting or another type of amplifiers? It's because VI is connected to the negative side of the amplifier. Okay. So here, how can we find the output? How do we solve this kind of circuit? How do we find the output? First of all, we will assume that we're talking about the ideal case of the amplifier. In the ideal case of an amplifier, the open loop gain, which is the gain inside the op amp, it's equal to infinity. That's one of the let's say assumptions in actually that's one of the values in the ideal case, and Vn is equal to Vp whenever we have an ideal amplifier. Okay, where's Vn? Vn is the voltage at the negative side. This is Vn and this is Vp. They are always equal to each other in an ideal case. So how do we solve V output? We always start from these 2 points, Vn and Vp. Okay, which of these two voltages do we have a direct value of? We know that Vp is equal to 0 because it's grounded. Okay, if Vp is equal to 0, this means Vn is also equal to 0. Now, after we have analyzed Vn and Vp, now we can find V output through nodal analysis. Nodal analysis at this point. Okay, now we will do nodal analysis. So we will say, let's write first nodal analysis at node Vn. Okay, so it will be Vn minus V input divided by R input plus Vn minus V output over Rf is equal to 0. And note that the currents here are also equal to 0. The currents that are being inputted to the amplifier, they are also equal to 0. Okay, they are always equal to 0. Okay, again in the ideal case. So here Vn, we said it's 0. Okay, so how can we simplify this? It will be as follows. It will be 1 over Ri V input minus 1 over Rf V output equal to 0. So 1 over Rf V output is equal to minus 1 over R input V input. V output is equal to minus Rf over R input V input. So what is the gain? V output over V input is minus Rf over R input. Okay, now note that this is equivalent to V output over V input is equivalent to minus K. The gain is, the K is the gain. This is the gain. Okay, this is the what? This is the gain. This is the gain, and the gain is negative. Okay, now because it's inverting, we got a negative sign. If it wasn't inverting, then we won't have this negative sign. Okay, so now we know how to solve an amplifier in general. Let's take an example. If we have this circuit and you were asked to find the type, this is R1 and R2, let's call it R1 and R2. Okay, and we were asked to find the type of the filter. Find type of filter. Now we know it's an active low pass filter, but let's prove it. How do we prove it? We said that we need to substitute in two values at omega equal to 0 and at omega equal to infinity. When omega equal to 0, we have only capacitor. So capacitor is equal to 1 over SC, which is equal to 1 over JWC, which is equal to 1 over 0, infinity, which represents an open circuit. Capacitor is equal to 1 over SC, 1 over JWC, 1 over infinity results in a 0, which is a short circuit. Let's now redraw our circuit with the following new values. Here we have R1, voltage source, V input. Okay, here we have R2, and our capacitor is open circuit. Open circuit. Now, what is the value of the output? We said that we need first to find the values of Vn and Vp. Yeah. This is 0. If this is 0, this is also 0. Okay, and now we need to do the analysis. 0 minus Vi over R1 plus 0 minus Vi output over R2 equal to 0. So 1 over R2 V output is equal to minus 1 over R1 V input. This will give us V output over V input is equal to minus R2 over R1. Now notice that the gain is always equal to what? The resistance, the feedback resistance divided by the input resistance. Okay, so this is the V output over V input. Let's do the same here. Okay, grounded. Here R1 with the voltage source V input, and R2 with V output, and the capacitor is short circuited. Now, if we have a short circuit parallel with a resistance, the resistance disappears. Okay. Okay. So now this value is 0. If this is 0, this is also 0. If this is 0, this is also 0. And as this is a only wire, then V output is what? It's 0. And if V output is 0, then V output over V input is 0 again. Okay, let's draw now the magnitude. When omega is equal to 0, what is the magnitude? It's minus R2 over R1. Actually, it's R2 over R1 because the magnitude has to be in the positive side. So it's R2 over R1. And when omega is equal to infinity, okay, the magnitude is what? 0. Okay, so this is the active low pass filter. Okay, so let me repeat again. Why did I remove the minus sign when I plotted the magnitude? The magnitude has the absolute values and it has to be positive. That's why I did not put the minus sign. And I also said that V output over V input is equivalent to what? Minus K. So what is the gain? The gain is only K. Minus is separate from the gain. Okay, according to this general rule. Let me highlight it. Okay, excellent. Moving on, let's find the transfer function. Find the transfer function of this circuit. The circuit was like this, minus positive. This is grounded, resistance R1 with the voltage source VI, grounded again, another resistance R2 in parallel with a capacitor. This is V output. Now, we need to find the transfer function, which is H of S, which is V output over V input. Okay, now in passive filters, what did we usually do? We usually start from V output and we do voltage division. But here it's impossible to do voltage division because of the op amp. So here we will solve it using another method or another technique. Now, if you remember, we said that V output over V input is equal to what? It's equal to minus K. And what was K? K was the top resistance or top impedance, let's say, divided by the bottom impedance. What does that mean? It means that the total impedance in this area divided by this impedance, the total impedance in this area, with a minus sign will give us the transfer function. So we will call this Z1 and this is Z2. Okay, Z1 is equal to R1, whereas Z2 is equal to 1 over SC multiplied by R2 over their sum, because they are in parallel. Okay, now what is the transfer function? The transfer function is minus the top impedance divided by the bottom impedance. This is the transfer function. Let's substitute now the values. 1 over SC multiplied by R2 divided by 1 over SC plus R2 divided by Z1, which is only R1. Now, before we convert this form into the general equation, which is minus K omega C S plus omega C, okay, we need first to simplify our equation, our expression. How do we simplify this? We have to simplify it by eliminating the denominator of the numerator. So we multiply by the same 1 over SC plus R2, the denominator, same value, multiplied by it, okay. This will give us what? It will give us minus 1 over SC multiplied by R2 divided by R1, 1 over SC plus R2. This is equal to what? Minus 1 over SC R2 divided by R1 over SC plus R1 R2. Right? Why do I feel I have done something wrong? No, I think everything is correct. Okay, let's move on. Now we have to convert this form into the general form. Okay, how do we do it? Now, I used to tell you that we need to focus on the S's. Okay, that's fine. But now in the active filters, we need to do something first before we focus on the S's. We need to focus first on the minus K. Once we fix the minus K, we can fix the S's later on. So the first thing is that we need to take out the minus K. Minus is ready. Now we need the K. What is K? K is the top resistance divided by the bottom resistance. Now, what's the difference here? When we did the transfer function, it was the top impedance. Impedance means total resistance, okay, divided by the bottom impedance, total impedance in the bottom. Whereas the K by itself, the K here is the top resistance, only R's, divided by the bottom resistance. Okay, so it's what? It's R2 over R1. So we need to put R2 over R1. Now we need to take R2 from the numerator and R1 from the denominator. So taking out R2 and R1, this will leave us with 1 over SC. And from the denominator, this will leave us with 1 over SC plus R2. Okay? Now, here, let's now focus on the S's. Do we have an S in the numerator? No, we don't have an S in the numerator, so we need to eliminate the S by multiplying by S in the numerator and denominator. This is equal to what? This is equal to minus R2 over R1 multiplied by 1 over C divided by 1 over C plus R2S. Okay? Now, S, the coefficient of S is 1. So we need to divide by R2. 1 divided by R2. And here we do the same. This will result in minus R2 over R1. 1 over R2C divided by 1 over R2C plus S. Okay? Now we're done with the transfer function. Now here note that omega C, as we said earlier, that it's what? 1 over RC. This is omega C. And this is what? This is the gain. Okay? Now we said that omega C is always equal to 1 over RC, but we have one C and you have two R's. Which R are we going to take in the omega C? Omega C is always equal to 1 over RC and the resistance that is with the capacitor. So any resistance that is accompanying the C is placed in the omega C. So here it's 1 over R2C and as you can see that R2 is with C. Okay? Great, let's move on. Let's take an example to solve. Here. Okay. So using the circuit shown in figure 15.1, which is a low pass filter, active low pass filter, it was an active low pass filter. Okay. Calculate values of for C and R2 that together with R1 is 1 ohm, produce a low pass filter having a gain of 1. That's weird. Why is this not clear? Gain of 1. Okay, there's a gain of 1. The pass band and a cutoff frequency of 1 again. Okay. Okay. So how can we find the capacitor, the value of the capacitor and R2? We know that the gain is always equal to the top resistance divided by the bottom resistance. Gain is 1, R2 is unknown, and R1 is 1. So R2 is equal to 1 ohm. Solved. Okay. So how can now find the capacitor? Another equation that we already know that the omega C is 1 over RC, which R that is accompanying the capacitor, so it's R2. Omega C is 1 and R2 is 1. Let's find capacitor. Capacitor is also 1 farad. Okay, so this question was simple. Let's move on. Let's take a look. Let's now analyze the active high pass filter. This is an op amp, grounded, capacitor, R1, VI, and it's grounded with another resistance, R2, and V output. Okay, let's find the type of the filter. Find type of filter. We will substitute in two values at omega equal to Z, at omega equal to infinity. Okay, now this value is 0, so this value will be 0. Actually, that's too early for the zeros. Okay, so where do we have omega? We have omegas in the capacitor. So capacitor is equal to 1 over SC, 1 over JWC, 1 over 0 is infinity, so it's an open circuit. Okay, let's do the same thing here. Capacitor is equal to 1 over SC, 1 over infinity is equal to 0, which is a short circuit. Let's redraw the amplifier. Negative, positive, grounded, R1. The capacitor here is open circuit, right? Okay, it's open circuit, R1 and V input. This is R2. Okay, so what is the output now? Let's see, this value is 0. If this is 0, then this is 0. Now we said that the current, there's no current, so R2 is useless, it's as if it's a short circuit, and if it's a short circuit, then the output is also 0. If V output is 0, then V output over V input is also 0. Let's check out the other case. This is a short circuit, so here R1 with V input, and here we have R2, V output. Okay, so if this is 0, this is 0. Okay, now we need to do nodal analysis. So 0 minus Vi divided by R1 plus 0 minus V output divided by R2 equal to 0. Okay, minus 1 over R2 V output is equal to 1. Let's take the minus on the other side also. Minus 1 over R1 V input, so V output divided by V input is equal to minus R2 over R1. That's it. Okay, so this is the value. Let's plot the magnitude. Omega with respect to the magnitude. When omega is 0, the magnitude is 0. When omega is infinity, the magnitude is what? It's R2 over R1. Be careful not to put the negative sign. Okay, so this is the what? This is the active high pass filter. Okay, let's now find the transfer function. Let's find an expression for the transfer function. Find expression for the transfer function. H of S. Okay, let's first plot the circuit, draw the circuit again so it's easier to refer to it. Capacitor with a resistance R1, P input, grounded, and here we have R2, V output. Okay, so H of S. What's H of S? H of S is V output in terms of V input. We said with op amps we need to break it into two parts, Z2 and Z1. What is Z1? Z1 is resistance in series with the capacitor, right? And Z2 is only R2. The transfer function, it's minus the top impedance divided by the bottom impedance, so it's minus Z2 over Z1, which is equal to minus R2 divided by R1 plus 1 over SC. Okay, now let's convert this expression into the general form of the high pass filter. The general form. Okay, it's H of S minus K S over S plus omega C. First we need to take out the minus K. K is minus K. K is the what? It's the top resistance divided by the bottom resistance. So it's R2 divided by R1. Okay. Now we need to extract those two resistances from the main expression. So in the numerator it will become 1 over 1 plus, we need to take out R1 from the second term of the denominator. There's no R1, so let's assume there's R1 over R1, which is 1, right? If you take out the top R1, you will left with the bottom R1. Okay, so here you will end up with 1 over SC and R1 at the bottom. Okay, so this is the general expression. No, still we're not done. Why? Because here we have a capacitor in the numerator, S in the numerator, and here we do not have an S, so we need to multiply by S. Okay, so now it will become minus R2 over R1 multiplied by S divided by S plus 1 over R1C. Now we are done. And to prove it, this is K and this is omega C. And as we said earlier, that omega C is always 1 over RC, and it's the resistance that is accompanying the capacitor. Okay, let's take an example for the active high pass filter. Copy, let's paste it in here. paste it. Okay, so compute the values of R2 and C that yields a high pass filter with a pass band gain of 1 and a cutoff frequency of 1 if R1 is 1. Okay, so first let's plot, or let's draw the circuit of the high pass filter. Here we have the capacitor with R1 VI, and here is R2. Okay, we know that K is always equal to what? The top resistance R2 divided by R1. The question provided us with R1 and K, so it's R2 divided by 1. So R2 is equal to what? 1 ohm. Okay. Now, we need to find C through the omega C equation. R, C, which are R that is with the capacitor. So omega C is 1. And R, we just found it to be 1. Actually, it was given the question. So C is 1 farad. This question is also simple. Now, let's take a more challenging question. Let's see. Cut. Paste it. Okay. Now, compute the values of R2 and C that yields a high pass. Was this? No, I think this is the same question. We copied the wrong one. Yeah, I need this one. Cut. Here we go. Okay. Compute the resistor values needed for the low pass filter circuit in figure 15.1 to produce a transfer function. Use 5 microfarad for the capacitor. Okay, so we have an active low pass filter. R1 VI grounded, R2 with V output in parallel with a capacitor C. Okay, and we have this transfer function. Now we need to find what? We need to find R's. So we need to find R1 and R2. Okay. Now we know that omega C is equal to 1 over RC, and R is R2. Do we have omega C? We do have it, but in an indirect way. Let me first write the general equation. Okay, it's H of S minus K omega C over S plus omega C. Now what is this value? This value is omega C, and this value is K omega C. Okay, so what is omega C? Omega C is actually 5,000. Okay, and the capacitor was given to us, it was 5 micro. If you compute this, you will get R2 to be equal to 40 ohm. Okay, now we need to find R1. How can we find R1? Through the gain. Gain is equal to the top resistance divided by the bottom resistance. We already computed R2, we need R1. But in order to find R1, we need K. How can we find K? From here, from the numerator of the transfer function. Okay, we know that K omega C is equal to 20,000 and omega C is equal to 5,000. So if we divide omega C, we will get the gain. So K is equal to 4 here. It's 4. R2 40 divided by R1, so R1 is equal to 10 ohm. Okay, we're done for this question. Let's move on. So far we have discussed the active low pass filter and the active high pass filter. Let's now discuss the band pass. Active band pass. Active band pass filter. Let's compare the magnitude of the passive with the active. Okay. For passive, the magnitude plot was as follows. We had two omega C's, omega C1 and omega C2. In the middle, or in the center, we had omega naught, which was called center frequency. The distance between omega C1 and omega C2 was called the bandwidth. Okay? The maximum magnitude was 1, and at omega C1 and omega, this is only a sketch. Okay? This is only a sketch. It was 1 divided by root 2. It was just the maximum divided by root 2. Let's fix this. Omega C1. Okay. Oops. This is omega C1. Okay. Now, okay, so what is beta? Beta was equal to omega C2 minus omega C1. Let's move on to the active. For the active filter, the magnitude plot is a bit different. Okay, it's like this. It starts low. Once it reaches the maximum, it stays on the maximum for a very long time and then drops again. Okay, so here we have omega C1, omega C2. This, if you remember, this was the high pass, the high pass filter of the band pass filter, and this was the low pass, right? Here we have the same thing also. This is the high part of the band pass, this is the low, and this is the inverting. If you remember, for the active, there are three components for the active band pass. There's a low, high, and inverting amplifier. Okay. Now the inverting is the one that will give us the gain. This is actually the gain. Okay. And in the center, we have the center frequency, omega naught. Now, what's the difference between active and passive? In passive filter, omega C2 and omega C1, there isn't a very big difference between them. Whereas here, omega C2 is way much greater than omega C1. Okay, so when we're calculating beta, it's omega C2 minus omega C1. But when you subtract a small number from a very large number, then you won't notice any difference. So as a simplification, you can just say beta is equal to omega C2 in active filters, because omega C1 is almost 0 compared to omega C2. Okay, I hope it's clear. This is beta. Okay, let's try to find the transfer function now. Plus grounded RL with the capacitor Okay, this is Vi. Okay, we have here another resistance R H representing high and L representing low. this is the inverting part. Okay, this is our F. Okay, so this is the active bandpass filter. Now, how do you find the expression for the transfer function? The approach of solving this kind of question is different. It's actually different, okay? So how are we going to find h of s? In order to find the h of s of an active bandpass filter, we will multiply the transfer functions of all the components. We multiply the transfer function of the low with the high with the inverting to get the bandpass filter, okay? Now, if you multiply the transfer function of low and high with the inverting, how many gains are we going to get? How many k's? We're going to get 3 k's, right? One in the low, one in the general, and one in the inverting. But the bandpass has only 1 k, and it comes from where? From this part of the bandpass, right? From the inverting. So we will multiply the general equation of low and high, but without their k's. So h of s will be omega c divided by s plus omega c. This is the low part multiplied by the high part, s plus omega c, multiplied by what? Minus rf over r input. Nice. Okay, so what is the general equation? It's h of s equal to minus k beta s squared plus beta s plus omega naught squared. Okay, let's first take out the k. Where's the k? This is the k. So we're going to say it's minus rf over ri. We're done with the k now. Okay, omega c divided by s plus omega c multiplied by s over s plus omega c. Now, let's multiply these two terms together and see what we will get. Minus rf over ri multiplied by omega cs. Okay. Now here we have omega c in the low part and in the high part. However, those two omega c's are not the same. One of them is omega c1 and the other is omega c2. In order to differentiate between them, let's plot the magnitude to help us. Okay. Now the active bandpass looks like this. We have omega c1 and omega c2. Okay. Where is the omega c1? Is it with the low side or the high side? Omega c1 is with high and omega c2 is with the low. Okay. So for the low, it will be omega c2, and for the high it will be omega c1. Okay, so here we have actually omega c2s divided by s squared plus omega c1s plus omega c2s plus omega c1 multiplied by omega c2. Okay, now we said that beta in active bandpass is equal to what? Omega c2, right? And what is this? This is actually beta. This is beta. And we said this is what? This is k. Okay. Let's rewrite it. Minus rf over ri beta s divided by s squared plus omega c, where I'm going to factor s out, s plus omega c1 omega c2. Okay, what is omega naught? Omega naught is equal to square root of omega c1 multiplied by omega c2. So omega naught squared will equal to omega c1 multiplied by omega c2. Hence this entire thing is omega naught squared. This means we are on the right track. Now this is the only thing left. Okay, omega c1 plus omega c2. We said omega c1 is almost 0 and omega c2 is equal to beta. So this is almost 0, and this is beta. Okay, so this entire thing will be beta. So if you rewrite this, you will get minus k beta s squared plus beta s plus omega naught squared, which is identical to this general equation. Okay, great. Let's take one final example before we conclude chapter 2. Okay. Here the question says we need to design. Design means find the unknowns. A bandpass filter, and we have for a graphic equalizer to provide an amplification of 2. Amplification means again of 2, so we're talking about an active bandpass filter with the band of frequencies 100 and 10,000, which is omega C1 and omega C2. Capacitor is 0.2 microfarad. Okay, before we proceed with this question, let's draw the active bandpass filter. This is grounded, RL, okay, V input, okay. Let's call them R1 and R2. Let's call them R1 and R2. R1 and R2. Here we have the capacitor C1, R3, C2, okay, RH, no, actually we'll call this R4 and R5, this is R6 and the output. Okay, so we were given k is equal to 2. We are given fc1, which is equal to 100 hertz. We are given fc2, which is equal to 10,000 hertz. We are given c, which is 0.2 microfarad. They did not specify what is c1 and c2, so we'll just equate both of them to 0.2 microfarad, and okay, that's it. Now we need to design. Okay, so how are we going to proceed? Let's see. Let's first convert fc1 to omega c1. Okay, this will be equal to 2 pi f, so it's 2 pi 100, which is equal to 200 pi rad per second. Omega C2 will be equal to 2 pi f, 2 pi 10,000, which is equal to 20 kilo pi rad per second. Okay, what is omega C1? What is the equation of omega C1? Omega C1, is it for the low or the high? Low, this is high, and this is inverting. Okay, now we said that the magnitude plot will help us identify which is which. This is the active bandpass, this is omega C1, this is omega C2, this is the high, and this is low. So for high it will be omega C1. Okay, so omega C1 is equal to 1 over R3C2. Okay, do we have R3? No, we don't. Do we have C2? Yes, it's 0.2 microfarad. And do we have omega C1? Yes, we do have omega C1. Let's substitute in values. 200 pi is equal to R3 unknown, and C is 0.2 micro. This will give us R3 equal to 7,958 ohm, which is almost 8 kilo ohm. This is R3. Now let's do omega. Let's write the equation of omega C2, which is for the low pass filter, the low part of the band pass. So it's 1 over RC, C1 and R2. Omega C2 is 20 kilopi. 1 over R2 is unknown and C1 is 0.2 micro. So R2 will equal to 80 ohm, almost 80 ohm. Okay. Now, we said that the gain is coming from the inverting part. So gain is equal to R6 over R5. Okay, let's keep this aside. What is K? K is 2. We know it from here. K is 2. Okay, if K is 2, what is the gain for the low side and the high part of the bandpass? They are equal to 1. They are unity gains. Okay, the gain for the low and high are always equal to 1. K for the low is always equal to 1 and K for the high is always equal to what? 1. The gain for the low part, it's equal to what? It's equal to R2 divided by R1. So let's write it down. K for low is equal to R2 divided by R1. K is equal to 1. R2 is unknown and R1, no, actually R2 is 80. 80. Actually, I should written this here and this should have been written here. Anyways. So 80 divided by R1. R1 is what? Equal to R2. It's equal to 80 ohm. Okay. Let's do the same thing here. K of high is equal to R4 divided by R3. K is 1. R4 is unknown, yes, and R3 is 7,958. So R4 is equal to R3, which is equal to 7,958 ohm. Okay, so now we have found all the resistances except R6 and R5. In order to find R6, we need first to know R5. Let's assume that R5 is equal to 1 kilo ohm. Okay, we are designing this so we can assume R5. A good assumption that R5 is 1 kilo. Okay, so K is 2, R6 is unknown, R5 is 1 kilo. So this will result in R6 equal to 2 kilo ohm. Okay, we're done with this question. Now, if we had another part saying, part B of the question saying, find the average power delivered to the load resistance at the cutoff frequency. Omega C. Okay? Omega not actually. Yeah, omega C. Sorry, cutoff center, that is. Okay. So what was, I gave you equation for power, I think in the first video of chapter 2, first or second, I'm not really sure. So the power was what? The power at the center frequency was P max divided by 2. Okay? And P max was equal to half V load maximum squared divided by the resistance RL. Okay? Now what is RL? Let's say that RL was given to us as 1 kilo ohm. Okay, it was given in the question. How can we find the maximum V output? Now we know that the magnitude is actually V output over V input. We want the maximum V output. V output max is equal to what? H max multiplied by V input. Okay, let's also assume that V input was given to us as 1 volt peak. So here the gain was 2, right? The maximum gain was 2 multiplied by 1. So the answer is 2 volt. The maximum V output is 2 volt. So to be half, don't forget the RMS. 2 divided by root 2 squared divided by 1 kilo ohm. This will give us 1 milliwatt. Okay, so 1 milli divided by 2 is what? It's 0.5 milliwatt. Okay, so now we're done with active filters and we are done with chapter 2. Thank you again for listening. See you later.